Okay, the final talk of this morning's session is given by Zeev Rudnick of Tel Aviv. Oh, okay, I forgot to say where Sandro is from Genova. A little late, better late than never. Says Zev's at Tel Aviv, and he will talk on eigenvalues of the hyperbolic Laplacian and random matrix theory.
Okay, so it's a pleasure to be here. Emmanuel started the tradition of using a slide with funny languages, and I decided to use one of the languages which are spoken in Montreal, but I would leave it to the end for people to guess what it is. So I want to discuss something that's been close to my heart for many years, but I will motivate it by a toy example, which is the Riemann Zeros. So I think in this audience, people know what the Riemann Zeros are, or at least where they come from. And we know that the Riemann zeta function has lots of non-trivial zeros, and in fact there is an asymptotic count of the number of zeros which lie in the critical strip up to a large height, and that's called the Riemann von Mangold formula. And it says that the number of zeros within imaginary part between 0 and t grows asymptotically, like essentially t log t, plus a remainder term. And the remainder term is small. It's bounded by log t, essentially. You can do a little bit better assuming the Riemann hypothesis. But in fact, the typical size is much smaller than log t. Selberg computed the variance of the remainder term, meaning the second moment of this function s of t, and he showed that it is growing like log t times a very specific constant. So typically, the size of the remainder term is square root log t. Now, I'd like to address the significance of this particular result in a more general context. So we think of this as saying that the zeros don't fluctuate very much; they're rigid. That is, this counting function essentially grows very smoothly with a very small fluctuating part. So I'll set it up in a general context. So I'm giving a sequence of eigenvalues. Let me put them on the line, right? The zeros all lie on the line. We just don't know how to prove it. And think of them as eigenvalues of some matrix. And then the number statistic is asking for the number of zeros in a window, and you think of the window as being random, and that means you take, for instance, the position of the window to be random with your favorite distribution. And then you ask, assuming that you take windows which are supposed in some expected sense to contain L zeros, you ask for the variance of this number, how it grows or how it changes with L being the important parameter here, the expected number of zeros. Or you can also average over your favorite set of random matrices once you've chosen what random means. There are lots of choices here. We'll see them later. Okay, so let's take 3 versions of what a random matrix means. The easiest thing is you just think of the matrix as a diagonal matrix where the entries are independent. So that just means you take random numbers on the ray line with a certain distribution, let's say uniformly distributed between 0 and t, and play this game. And then, as is well known, the fluctuations are going to be of square root type. So the variance will grow like L being the number of expected zeros. So very large fluctuations. If you take a a random real symmetric matrix where the entries, let's say, are Gaussian. And it turns out that the variance of this statistic is much, much smaller. It grows logarithmically with L instead of linearly with L. Or you can play the same game with eigenvalues of complex Hermitian matrices, or my favorite example is of random unitary matrices, and that's easy to think about because the set of all unitary matrices forms a group, and it has a unique probability measures, and that's what random will mean. So you will average over the unitary group and play this game, and then you will find also that the variance, instead of growing like L in the Poisson case, will grow like a constant times log L. But the constant is actually 1/2 less than the constant for random symmetric matrices. And that 1/2 is actually very crucial for me later. And what we will see is what transpires is that this complex Hermitian matrices or random unitary matrices are exactly what is predicting the answer for the Riemann zeros. Now, of course, this is somewhat uninteresting because that answer was known from the 1940s. As I said, it was due to Selberg, who computed this analogous quantity for the full range, and then Fuji looked at short interval results. And after you make the translations, after you translate from Selberg's language to this language where the only parameter is the expected number of zeros, you find that what Selberg and later on Fuji proved is that the variance of the Riemann zeros in short intervals behaves as though they are eigenvalues of a random unitary matrix. There are numbers here, but this is how you should think of the results here. Okay, and you see here a plot that affirms that the theorem actually is backed by numerics, that numerics converge very quickly. And you see the top plot is GOE, the random symmetric matrices. And then there's the lower plot, which is the dashed line is GUE, which is unitary matrices. Okay, there's another plot which is not important for me. Okay, so as I said, this for me is a toy model. I am more interested in the eigenvalues of the Laplacian instead of the Riemann zeros. So let's take a surface, compact surface, and put a Riemannian metric on it. And once you have a Riemannian metric, you have a Laplace-Beltrami operator, and you have eigenvalues. In fact, you have lots of eigenvalues. And for a surface, the analog of the Riemann von Mangold formula says that the number of eigenvalues up to E grows linearly with E, with a prefactor that tells you what the area of the surface is. This is called Wahl's law. So the type of surface I have in mind will be, for instance, a sphere, a round sphere, where the eigenvalues, you can just write them down. There are integers with high multiplicities. Or a flat torus, where again, the eigenvalues are essentially integers. For instance, there are sums of two squares, or they could be the values of a binary quadratic form. Or another example, and that's the one that is of interest to me, is to take a hyperbolic surface, meaning a surface of higher genus where you put a metric of constant negative curvature. So the question is, what does the number variance look like in those cases? And there's what for me is a fascinating conjecture that says that if you take short enough windows, then for some special cases, such as flat torus, the variance will go like the eigenvalues will a Poisson sequence. While if you take a chaotic surface, for instance, a hyperbolic surface, a surface with a metric of constant negative curvature, or just negative curvature, then the variance will behave as though you have eigenvalues of a random symmetric matrix. So in particular, the variance will be very small. And this is what I want to examine. So I should say until now, there is no proven case of this chaotic in this chaotic setting. It's something that looks very, very difficult. So let me focus on the case of hyperbolic surfaces. It's a chaotic case. So you take, as I said, a surface of higher genus and then put a metric of constant negative curvature, let's say curvature -1. And such a surface in formalization theory says that you can present it as the quotient of the upper half plane by a discrete group of hyperbolic isometries. For instance, you can take a look at the disk model of the Euclidean geometry, and here is you see an example here of a genus 2 surface where the fundamental domain of this uniformizing group is an octagon. And again, Wahl's law is something that works for any surface. In particular, here, if you couple Wahl's law with the Gauss-Bonnet theorem, it will say that the number of eigenvalues grows linearly with the energy, and the prefactor is just the genus -1, because that turns out to be the area over 4 pi. And this case is the case of hyperbolic surfaces is analogous to the Riemann zeta function case, because the eigenvalues turn out to correspond to zeros of something called the Selberg zeta function, and the role of primes in the Selberg zeta function is played by primitive closed geodesics, whatever they are. But unlike the Riemann case, where the zeta function seems to be the primary object, here it's a sort of secondary object, and it's not very useful to work with it directly. Okay, so here's some numerics that were done actually 30 years ago. People based in the physics community. This is the real quantum stuff, not this toy thing. So they took 30 different genus 2 surfaces, meaning they prescribed the fundamental octagon and computed for each such surface 150 eigenvalues. You have to break them up into symmetry classes because a genus 2 surface is hyperelliptic. There's a hyperelliptic involution, and then the eigen, it commutes with Laplacian, and you have to break up the spectrum into even odd parts. And so you get, they got a set of 60 matrices, let's call them like that, each containing 75 eigenvalues. For each of them, they played this game of computing variance, and here is the picture. And so the solid line is the data, and then there's a straight line, which is Poisson. That's clearly irrelevant. There's the GUE line, which is the bottom one, which is also not relevant. And the GOE line, the random symmetric matrix line, that seems to be the closer, the good fit. So at least, and again, the conjecture was that for sufficiently short interval. And so this matches well the conjecture. So this is a good, there's good support for this conjecture. The numerics are not very good because it's not so easy to compute eigenvalues for these hyperbolic surfaces, and so they were using a finite element package. Not package, they adapted it, but you can do better if you want to today. But I like this picture. You can do better, but nobody's done. Now, it turns out that the picture is misleading because there were known counterexamples to this conjecture. They were known to Selberg, but not to the physicists initially. And this is, the key word here is arithmetic. Selberg computed the variance analogous to his computation of the variance of the second moment of S of t for the Riemann case, for a special example of a hyperbolic surface, which is essentially SL2Z. Think of it as SL2Z, okay? And he found that the variance is growing very, very quickly, as it would essentially in the circle problem. He could only get the lower bound, and that's all we can do to date. But that's completely incompatible with this logarithmic type behavior that you expect, that you saw numerically, and that you expect based on random matrix theory. And then when Gilou and Peter Sarnak went back to this 20 years later, and they extended this to all arithmetic surfaces. You need a new idea though, because SL2Z has a special property that the primes are the analog of primes are well separated, which is not the case for general arithmetic groups. But in any case, they also show that the number variance is very big. Its lower bound is compatible with the Poisson type statistic. There's no upper bounds known here. But the lower bounds already say that you cannot expect this conjecture that any chaotic surface, any chaotic system, I mean, the quantum mechanics have the random matrix type theory behavior is not going to work. Okay, so there are counterexample. What can you do? But we still believe, I showed you the numeric, that if you take a generic surface, then you will have this random matrix type behavior for the number variance. Let's believe it's backed up by numerics. And this is what I want to pursue. So what I want to do is to take the space of all hyperbolic surfaces of genus 3. This is what I want to do in my dreams. I mean, many people have been wanting to do this. You would also want maybe to average over the space of all negative curvature surfaces of genus 3, but that's an infinite dimensional space, and I don't know how to average over such things. But hyperbolic surfaces of fixed genus turn out to be a finite dimensional space whose dimension is 6G minus 6. And it actually is a nice structure. It turns out to be the quotient of a Euclidean space of that dimension by a discrete group called the mapping class group. It's a non-compact space, but it's better to think of it as a compact, just like a compact quotient. And there is a natural probability measure on that space called the Weil-Peterson measure, which is what you want to average about. I'm not going to give any details because it's not number theory, it's the wrong audience, and it's not good to do it, and people want lunch. So, and John stole 5 minutes from my talk. So.
You have till 5 after.
No, but people will be mad at me. But so here's a baby version of this moduli space, but not for higher genus, which would be hyperbolic surfaces, but for genus 1, which are flat tori. And everyone here knows this example. Okay, so the way you do this, and this is a model for what you do in higher genus, you want to look at all the space of all flat tori up to isometry. And you also can introduce scaling, unlike the case of negative curvature. So if you identify two flat tori up to rotation, reflection, and scaling, this is your moduli space. It's called, okay, let me stop here. So every flat torus is the quotient of the Euclidean plane by a lattice. And you first rigidify the situation and you form the analog of what in negative curvature would be Teichmuller space. So you look at the flat torus, meaning a lattice, with a choice of basis for that lattice. So that's a bigger space. It's called the marking. And then after scaling and rotating, you can get the first basis vector of the lattice to be just a standard unit vector. Then the second would be any other vector that's linearly independent. And after reflecting, you can assume it lies in the upper half plane. And therefore, this Teichmuller space is just the upper half plane. And then you say, okay, the same lattice has many different bases, and that's a freedom that you account for by the modular group. And so in this case, the moduli space is just a quotient of the upper half plane by SO2Z. So that's a picture that we all know and love, which is the fundamental domain of SO2Z. So this is the moduli space. This is a picture of a moduli space of not hyperbolic surfaces, but of flat tori, the genus 1 case. And the higher dimensional case, the higher genus case, sorry, is more or less similar, but more complicated. So I'm not going to describe it. So let me just say what the result is. So, oh, one more thing. On this moduli space, on this hyperbolic triangle, we still have upon the hyperbolic measure, dx dy over y squared, and that gives you a measure, a finite measure on this triangle. And once you normalize, you get a probability measure. And that's how you sample, that's how you average over the space of flat tori. It's very explicit. Depends what function it is that you want to average, but it's an explicit thing. And in higher genus, there is something like that, which is more complicated, but still turns out to be quite explicit. Okay, so I want to show that the number variance, when you average over all genus 3 surfaces, has this random matrix type behavior. Now, for reasons of harmonic analysis, I am not able to do the exact number statistic, but instead I engineered a smooth counting function that will mimic it. It counts eigenvalues in a window near energy, but with an analytic weight. And you can play this game in random matrix theory too. And for that, in that game, which has been played, this was a popular thing by, for instance, Dyson and Mehta 60 years ago. The variance of such a statistic turns out to be a constant, which depends on the window function with a very specific constant. So if you play this game for random symmetric matrices, you get twice some functional, and if you play it for random Hermitian matrices or random unitary matrices, the constant 2 is removed. So you can, this is a good diagnostic of which random matrix, which flavor of random matrix theory you are at, because it distinguishes between GOE, and definitely between those and Poisson, because for Poisson, the variance of this linear statistics still grows with the expected value. Yes, Leo. The integral, I am assuming that f probably integrates to 1. Yeah, you're right. So no, so L is the expected number of levels. Yeah, so this assumes that f integrates to 1. Yeah, the window function is a window function. It integrates to 1. But this quadratic functional is what it is. And there's a factor of 2 or 1, depending on if you're GOE or GUE. And in the Poisson case, the variance is linearly with a number of eigenvalues, while in the GOE case, the variance saturates the constant value. There's no fluctuations, essentially. Okay, so I want to take this functional, this linear statistic, which I said is a good diagnostic of which random matrix theory flavor I'm at, and average it over the moduli space of surfaces of genus G. And here's the result. So just ignore the red part. The result is that in this universal regime, the variance of this linear statistics is the same as for random symmetric matrices for the GOE. So this is how you should think of this result. But if you see what's written in red, I can't do what I wanted to do. I can't average over genus 3 surfaces. So I have to take a larger genus limit. And the order of limits is absolutely crucial for what I do. So there's a statement here, which I prefer not to read out loud. So just so if you fell asleep 2 minutes ago, then you will find out. Then you will think I did something actually better than I succeeded in doing. But in any case, the bottom line for me is that I have finally been able to find agreement with random matrix theory in the spectrum of hyperbolic surfaces, with this little caveat that I have to take a large genus limit first. Now, why was I able to do this? There's a new ingredient that was only became available a few years ago, and this is the work of Mariam Mirzakhani on simple closed geodesics. So let me just present a sample of her work, and something that is useful for me. Let's go back, this is the right audience, to the theory of primes. So in the theory of primes, we know the prime number theorem, which says that the primes become sparser and sparser, and the density of primes near x is 1 on log x. So if you take an interval of length lambda times log x, you expect lambda primes in there. And standard conjecture is that if you take this interval to be random of length lambda log x, then you will have a Poisson distribution for the number of primes in such intervals with parameter. And what Mirzakhani and Petri proved was that if you play this game with closed geodesics on a random surface, then in the large genus limit, you have a Poisson distribution. So it's the exact analog of this Poisson distribution for primes in critically short intervals. So this is the kind of ingredient that is useful when you try to prove things about eigenvalues. So I'm not going to get into this. Let me just summarize. So I showed you this linear statistic, the smooth linear statistic, which was engineered to be a good distinguisher between various flavors of random matrix theory. For the Riemann zeros, it's a good exercise to do to compute the variance of this linear statistics, and you'll get this funny quadratic functional of f. And what I showed for the moduli space of hyperbolic surfaces, at least in the large genus limit, you get agreement with random symmetric matrices. And the challenge is to do this A for genus 3 or genus 10, your favorite fixed genus. With 2, you have to be a little careful. And a much greater challenge is to do it for a fixed surface, but there you have to be careful. There are counterexamples. These are arithmetic surfaces. Okay, so happy birthday, Andrew.
Thank you very much. Is there any question, or everybody wants lunch?
Yeah.
Any questions? Yes.
There are people have thought about this. For arithmetics of like SL2Z, for SL2Z, you can actually execute this. It's a bit painful, but you can actually prove analog of twin prime type things with the hard deliverable type thing. But for generic surfaces, you don't have any arithmetic. It becomes we don't know what happened. This theorem of Mirzakhani that I displayed 2 slides ago does the job, because it says that much more than the hard deliverable type conjecture. It says that the length of closed geodesics actually give you a Poisson process on the line. But this is for random surfaces, not for a fixed surface. It's actually quite good in the genus. I get something like 1 over the genus. It's quite good. That's not. I have to take the large genus limit. That's the issue. There are people. There's a lot of work in the last couple of years where people, instead of looking at large eigenvalues, are focusing on the on the first eigenvalue because of expansion and Riemann graphs. And some people have schemes of trying to get expansions in powers of 1 over the genus in order to be able to penetrate this. This is the analog of Selberg conjecture, but I haven't seen this work yet. But for me, I was happy not to need any of this. Yeah, so what in fact, so let's go back to the Riemann zeta function. You know, it's my favorite example of the Riemann zeta. Selberg actually proved the central limit. So he didn't just compute the variance. He actually, once you normalize, he proved that there's a Gaussian distribution. I mean, it's a strange thing. He computed all moments, or all even moments, but didn't know and they were Gaussian. He didn't know that it's implied that there's a Gaussian distribution. You know, this was a few years ago. I can do the same thing here. I can compute all moments. It's just some combinatorial thing. Yeah, but I can do that. I didn't state it because time is short, and so this would be joint work with Igor Wigman that hasn't been written up yet. But there's actually a short way to do this without doing a lot of combinatorics. If you know some fancy probability theory, it gives a Gaussian. Again, in this funny limit where you take two iterated limit, and the order is very important. But you get. I prove that all the higher cumulants are zero. That's equivalent to a Gaussian.
Well, let's thank once again the speaker and all the speakers of this morning's session.